Okay. So, we are looking at logic programming and we were looking at Prolog, and in particular we were looking at the cut operator in Prolog. Now, what the cut operator does is that it kind of exploits the fact that Prolog searches the knowledge base in a depth first fashion, right. By this we mean top to down in the clauses that we have written, and if you have a set of goals to solve, then left to right. So, typically a Prolog cut operator is used to improve efficiency. So, we may have a program like this, for example, if you say if you remember some, we had tried to define happiness at some time. We had said that if x is happy, if x has eaten well. So, E stands for eaten well, and let us say we put this cut operator here, and then if x has slept well essentially, and the other clause we had was that x is happy if x has finished his assignment and has played something, let us say in the evening or something like that essentially. Now, if we have these two sentences, and the only difference is this time we have a cut in the first sentence, the cut operator, which is denoted by this. And the first thing about cut is that it always succeeds. As a predicate, it is a predicate and it always becomes true, but when it becomes true, it has a side effect. And what is the side effect? Is that you commit to goals on the left of this thing. What does it mean in this context? That for example, if we have a query, it says so let us say we will put question mark to denote a query, just like Prolog does. Let us say we are talking about a specific individual, let us say Suresh. So, we are asking whether Suresh is happy, whether this goal is true, and then it calls these three goals. Has Suresh eaten well? Supposing this goal becomes true, then it will move to the next goal, which is cut, which we have said will always become true, and then it moves to slept well. So, once you have crossed the cut, there is no other way you can try to show that Suresh is happy. Only if you can show that Suresh has slept well. So, at this point, if Suresh is true, then happy Suresh is true, and else it is false. even if we had in our knowledge base these facts that eaten Suresh and finished assignment Suresh and played Suresh essentially. Even if we had these three facts in our knowledge base, if we ask the question is Suresh happy, because of the fact that eaten Suresh becomes true, you get the program commits to showing that the only way to show happy Suresh is to now show that slept Suresh is true. So, if this is not true, then you return false essentially. You do not go and try the next way of trying to show happy Suresh, and that is the effect of cut essentially. Let us look at some examples. So, it might have occurred to you that in this program maybe that is not what you intended. You were trying to show that there were two ways that Suresh could be happy, either if he had eaten well and slept well, or if he had finished the assignment and played a game. But this program is not allowing you to do that. It is saying that if you have eaten well, then you can't use the other clause in which you had said that you finished the assignment and slept well essentially. So, one often distinguishes between two kinds of cuts. So, one is called a red cut, the other is called a green cut. Now, a green cut does not change the semantics or meaning of a program, whereas a red cut changes the meaning. So, ideally you should use only green cuts. It is used only for efficiency purposes. And basically it is dependent upon the search strategy. So, let us look at a example of a slight variation in a program, where one program uses a green cut and the other program uses a red cut essentially. So, let us look at an example here. Let us say you want to write a program to determine the maximum of two numbers. So, you are given two input and you have to decide which of them is maximum, and the schema is that x, y, z means z is equal to max x, y. This is what you want to compute, that you are defining a predicate of 3 arguments, where the third argument should match the maximum of those two. So, for example, if you give max 3, 5, 5, it will return true, but if you give max if you give a statement max 3, 5, 7, it will return false, and so on essentially. Only when z is equal to 1 of x and y, but it must be equal to the maximum of those two elements, this should return true. So, essentially we are defining a predicate where we can define max. So, one way to do it, and this employs a red cut, is as follows, that I could say max x, y, x. So, remember that these are variables, even though I have not put the question mark here. If x is greater than equal to y, and then I am saying I am putting a cut there. really. Essentially what I am saying with the cut here is that if you know that x is greater than y, greater than or equal to y, then x must be the maximum of those two elements x and y. So, you are done with the job and do not try anything else, essentially that is what you are saying with this cut. And then I am making this statement max x y y. So, I am writing these two statements. Remember that now this is trying to rely on the fact that Prolog searches in a particular fashion essentially. So, it will first look at the first statement, then it will look at the second statement essentially. So, on the surface there is no flaw with this program. For example, if you give a query like max 2 3 3, it will say yes and it will say 3 is the max, it will return the value or something, assuming it is returning the value. If you say max 2 1, sorry, I wanted to give a variable. So, it is x, so x equal to 3, 2 1 1, it will again say yes, because it is saying that the statement is true, and it will also say x equal to 2 in this case. So, in both the cases it will return a correct value to you, which is the maximum of this. So, on the surface it looks like this program is working correctly. As opposed to this, I am making a claim that this version of max, which I am writing in green color, uses a green cut. It also uses a cut, and it also has a similar second statement. So, either it is x or it is y. The first statement will be true if x is the max, the second statement will be true if y is the max as before, except that I put a condition again, and this time I explicitly ask that y should be greater than x. So, the first statement is saying that x is the max of x y if x is greater than or equal to y, and then do not do anything else. This do not do anything else is only to the Prolog interpreter, because that searches in a top to down and left to right manner. We are essentially saying that you are done by showing max and you do not need to show anything. The second statement says that y is the maximum of x and y provided y is greater than x. Now, you can see that I do not have to write greater than or equal to, because the equal to case has been taken care of in the first statement essentially. So, it looks on the surface that both these programs are identical, except that the program in the green has one extra test, which is that it will only say that y is max if it knows that y is greater than x. The program in the red will say my y is max if it knows that x is not the max, essentially in some sense. So, how does that change? So, one thing that you must kind of try to realize is that when we say that it does not change the semantics or it does not change the meaning of a program, we are saying that the fact that we are using cut in conjunction with the depth first strategy, we are not, it does not change the meaning of the program, because in pure logic programming the answer should not depend in the order in which you look at clauses essentially. It is purely a logical consequence that we are talking about essentially. So, the logical consequence should not depend upon the order in which you try the different rules essentially. But Prolog, because it does in a particular fixed strategy, we are trying to exploit the fact that we know in which order it will look at things to try to make things more efficient. And if we do that, then it is a green cut, but if we somehow change the program, then it is a red cut.
That if it is false, then the max x is not max. How can we infer that y is the max?
If x greater than y, if x greater than or equal to y,
The first proposition will be false.
it returns false.
Yeah. So
when will it return false?
So it will say that x is not max. So how can we say that then y is max?
No, but when will this x greater than y be false? when y is max. That is why in the second statement we are confidently saying that y is max. But I am still saying that it is still a red cut, because it can still change the meaning of a program, and I will give you an example in a moment as to of a query where you can see that this is happening essentially. Okay, so, we have looked at these two algorithms, one in the green, which I said was a green cut, and this one in the red, which I said was a red cut. For the two examples that we are looking at here, which is where the query has a variable x, there is no problem. The first query, when we have 2, 3 and x, returns yes, and it says x equal to 3 is the answer. So, 3 is the maximum of 2 and 3. For the second query, when we give a different order 2, 1 and x, again it finds this thing. Now, the first query, the second query gave an answer because of the first clause. It matched the first clause. So, x matched 2, y matched 1 and x matched 2, because it has to be the same value there, and then it returned the value 1. The second query gave an answer because of it matched the second one, which said that 2, 3 x, then y, the second one is the max essentially. So, 2, 3, 3 x, y, y will match 2, 3, 3 and 3 will be the answer essentially. But what if I give a propositional query? What is the maximum of 3, 2, 2? So, essentially when I give a propositional query, I expect a true false answer, what is more, I expect a correct answer, and this is what we mean by saying that a red cut changes the meaning of a program essentially. Now, if you looked at pure logic programming, and if I said that 2 is the maximum of 3 and 2, then the answer should be no, an emphatic no in fact. But what will the program in the red do? Now, let us look at this. The first clause will not match, because these two values are different essentially. For it to match, these two values must have been the same. So, but it matches the second clause. And answers yes, which of course is not a correct answer, and the reason for that is that the second clause is not explicitly checking that y is greater than x, whereas in the red cut version we had an explicit check which said that y is greater than x, and only then y is the maximum of x and y. This one is simply saying that if x is not the maximum of x and y, then y must be the maximum of x and y, and it does not really care whether it is really the maximum or not essentially. So, this illustrates the fact that a red cut can result in some cases in changing the meaning of the program, which results in wrong answers being generated, as in this example here. So, for this query, the red program will return yes, which is wrong, and the green program will return no, which is correct essentially. So, let us focus on green cuts for a moment, and let us look at this example where it really helps. So, remember that we had written this program to define an American cousin. Let us say that is the definition. So, AC stands for American cousin, X is the American cousin of Y if or Y is an American cousin of X if Y is a cousin of X and American Y essentially. Let us say that this itself was called by another clause which said that visits X Y if Y is an American cousin of X and invites Y X, some program which calls American cousin essentially. Now, we want to see what Prolog is going to do here. Let us say we have a query that does visit John. Let me use a question mark again. I am not doing it consistently, but still. So, does John visit somebody essentially? And then this will spawn two goals, that does John have an American cousin who invites him. The first one will in turn spawn these two goals. Does John have a cousin, and is that cousin American? And did the cousin invite John essentially. So, we have these three goals essentially. Now, just imagine that this is our knowledge base. So, we have John, and let us say Mary is a cousin of John, which means that they have a common grandparent. So, let us say this is a definition of cousin. First of all, X must not be equal to Y, then they may not be siblings. And then there must be a grandparent of X who is also a grandparent of Y. So, there must be some Z who is a grandparent of X and who is a grandparent of Y. So, assuming that the meaning of that G P X Z is that Z is a grandparent of X essentially. Okay. So, we are making this query about John, and then we are trying to first test whether Mary is a cousin of John, and to test that we will need to look at their family tree. So, let us say we have this person is father of John, this person is mother of John, and this person is father of Mary, this person is mother of Mary, and let us say this person is father of John, this person is mother of sorry mother of father of John. Maybe I should have drawn this a little bit differently. So that's the relation between them. Should have drawn it a little. So let me just draw this again. So father of John, mother of father of John, father of mother of John, and mother of John, and so these are the parent relationships. And let us say, as it can happen sometimes, that this is the relationship between them, that the parents of John and Mary are siblings essentially. I wonder whether I am doing something wrong here. Okay, both the mothers are children of this couple, and both the fathers are children of this couple essentially. So let us say it is a very closely knit family or something like that. Now, to show that Mary is a cousin of John, you will need to show that they have a common grandparent, and you can see that this path will work. That the father of John is also the father of father of Mary essentially. So this path in the black will work, and therefore we know that John and Mary are cousins. So this cousin will become true with Z equal to Mary, and then let us say Mary is not American. Now, what does Prolog do when it is trying to look at these two goals here? It is trying to show that Mary is an American cousin of John. So, first it shows that Mary is a cousin of John, and it shows that because we have seen along these black lines that both their fathers are sons of one person. So, they are cousins essentially. So, the cousin John Mary succeeds, but American Mary fails. So, let us say Mary is not an American. What does Prolog do? It comes back to cousin X Y and tries to show again that cousin John Mary is true, and it can do that because there are, I can see at least 4 different ways of showing that they are cousins essentially, because they have 4 common grandparents essentially. All 4 grandparents are same for both of them. So, it essentially it will try to show this cousin in a different way essentially. So, it is going to be doing useless work essentially. It will try with so first it has tried with this, then it will try with this, then it will try with this, and then it will try with this, and in all 4 times, because we know that Mary is not American, the second goal will fail anyway, and so it would have done some useless work, and then it will go and try for somebody else, whether John has another cousin who is an American and so on and so forth. So, to avoid this repetition, we can rephrase that program as that if an American cousin of X, Y is an American cousin of X, if y is a cousin of x. So, if you already know that y is a cousin of x, then you are committing to this part of the proof, essentially saying that we already know that y is a cousin of x. We put a cut here and then we test whether y is American or not, essentially. This means that once you have found out that John and Mary are cousins, you are not going to try any other way of trying to show that they are they are American cousins, essentially. Either Mary is American, in which case that American cousin will return true, or she is not American, in which case it will return false, essentially. So, here it is a case where it is useful, essentially. And in the last class, we had when we had introduced cut, we had seen that that was another interesting use of the word cut, essentially. So, let us look at another example, and we want to express the fact that Suresh likes all dosas except, let us say, onion dosa, if there is such a thing. So, we can do it like this: likes Suresh x. Let us deal with the exception first. If x is an onion dosa, then return fail. Remember that once you have crossed the cut, you are committed to the second part of the this thing. Then you can say likes Suresh x if, as long as x is a dosa, then Suresh likes it, essentially. But because Prolog will first look at the first clause, if the dosa happens to be an onion dosa, he would sort of not like it, essentially. And then you can give definitions for dosa. A dosa is a so basically an onion dosa is a dosa or masala dosa is a dosa or lava dosa is a dosa, and maybe you have other kinds of dosas, it does not matter, essentially. And if you have a knowledge base like this, and then of course, you give names to specific dosas, you say something like a, you define, for example, a small knowledge base in which you say onion dosa A, masala dosa B, C, and then you ask the query, does Suresh like anything? Then with this set of rules, it will return first masala dosa, in the sense that it will not be able to show that A is true, but for B and C, which are masala dosa and rava dosa, it will return the answer as yes, because the first goal would have failed. So, B is not an onion dosa, and therefore, it will try the second one, and it will test whether B is a dosa, and to test whether B is a dosa, it will see that because it is a masala dosa, it is a dosa. So, he likes all dosas except onion dosas, essentially. Okay, so I will stop here. We will stop looking at backward chaining here, and in the next class we will see what is a drawback of backward chaining, which is also a drawback of forward chaining, and then move towards general resolution.